Before proceeding with this video, you should open the Definite Integrals video capture sheet provided. You will be asked to complete tasks in the document throughout the video. This section is called Indefinite Integrals. We will be finding antiderivatives of basic functions. Let's start with our exploration from the discussion board. For each of the following functions, you are asked to find the antiderivative. Here are sample answers to the 6 problems on your capture sheet. The answer to number 1, f of x equals 2, is capital F of x equals 2x. The answer to number 2, lowercase f of x equals x, is capital F of x equals 1/2 x squared. The answer to number 3, lowercase f of x equals x squared, is capital F of x equals 1/3 x cubed. The answer to number 4, lowercase f of x to the negative 1, is capital F of x equals the natural log of x. The answer to number 5, lowercase f of x equals x to the negative 2, is capital F of x equals negative x to the negative 1. The answer to number 6, lowercase f of x equals x to the negative 3, is capital F of x equals negative 1/2 x to the negative 2. Notice that we always check our answers by taking the derivative of uppercase f and see if we get lowercase f. Remember that when we find the derivative, we always multiply the exponent by the coefficient to get the new coefficient. And we subtract 1 from the exponent. Did you notice that when we found the antiderivative, we always added 1 to the original exponent? And when we found the antiderivative, we always divided by the new exponent? The one exception is f of x equals x to the negative 1, which we'll address in a moment. Press pause now and make any corrections to your capture sheet. Let's take a look at our first discussion board question. What patterns did you see in these antiderivatives? Were you able to write a rule? We addressed this question on the last slide, where we noticed the following rule. If f of x equals x to the n, then capital F of x equals x to the n plus 1, all divided by n plus 1. But we saw that didn't work for all our examples. We can't divide by 0, so this formula can't work when n equals negative 1. So what was the antiderivative of f of x equals x to the negative 1, or f of x equals 1 over x? You may remember that the derivative of the natural log of x is 1 over x, so the antiderivative of 1 over x is the natural log of x. If f of x equals 1 over x, then capital F of x equals the natural log of x. But there's one thing we have to think about. What if x is negative, since the natural log of negative numbers is undefined? To take care of that, we take the absolute value of x. Take a moment and make any additions or corrections to your capture sheet. Pause the video to do so. Could a function have more than one antiderivative? The second discussion board explored that question. You are asked to choose one of the functions from the exploration and try to find additional antiderivatives. What are 2 or 3 more antiderivatives? I chose f of x equals x squared. If f of x equals x squared, then capital F of x equals 1/3 x cubed. Or capital F of x equals 1/3 x cubed plus 2. Or capital F of x equals 1/3 x cubed plus 1. Or capital F of x equals 1/3 x cubed minus 1. All of these are antiderivatives of x squared because the derivative of a constant is 0. So it turns out that the antiderivative of a function is actually a whole family of functions that are just vertical translations of each other. To summarize, a function capital F is an antiderivative of lowercase f if capital F prime of x equals lowercase f of x for all x. And now we have discovered that capital F is an antiderivative rather than the antiderivative, because any constant c can be added to get another antiderivative. We saw last week when we learned about the fundamental theorem of integral calculus that we can compute definite integrals by using antiderivatives. When we want to talk about antiderivatives separately for their use in computing definite integrals, we can use a similar notation and language. The family of all antiderivatives of a function f of x is the indefinite integral with respect to x and is denoted by the integral of f of x dx. If f is any function such that f prime of x equals f of x, then the integral of f of x equals capital F of x plus c, where c is an arbitrary constant. Notice that an indefinite integral is a function and a definite integral is a number. Using this new language and notation for the rules we wrote from the discussion board, number 1, the integral of x to the n dx equals x to the n plus 1 all over n plus 1 plus c, where n doesn't equal negative 1. And 2, the integral of x to the negative 1 dx equals the natural log of the absolute value of x plus c. Pause the video to copy down the first two properties of indefinite integrals on your capture sheet. Example 1, find the indefinite integral of 3x squared minus 2x plus 1. Pause the video and try this problem on your capture sheet. The integral of 3x squared minus 2x plus 1 equals x cubed minus x squared plus x plus c. Remember, you can always check by taking the derivative of your answer. Notice that we are essentially finding the antiderivative of each term. Or really, we're copying the constant and the operation and finding the antiderivative of each power of x. It equals 3 times 1/3 x cubed minus 2 times 1/2 x squared plus x plus c, which is the same as 3 times the integral of x squared minus 2 times the integral of x plus the integral of 1. Our example demonstrates the additional two rules, which look a lot alike our rules for definite integrals. The integral of f of x plus or minus g of x equals the integral of f of x plus or minus the integral of g of x. The integral of k times f of x equals k times the integral of f of x for any constant k. Pause the video to record these additional properties on your capture sheet.